It's essentially an academic talk, so apologies for that. But this is joint work with David, whom some of you met at the category theory tutorial, and some other folks at MIT, Patrick Schultz and others. And the goal of this talk is to describe a new, quote-unquote, algebraic way to formalize databases, queries, and other things related to them. And I won't spend too much time talking about what algebraic means, but the genesis of this project was that category theory itself was invented after World War II as a way to migrate theorems from one area of mathematics to another. And then David and some other folks at MIT realized that you could use category theory to migrate data from one computer system to another. So this whole talk is about using category theory to reason about and manipulate data. And in addition to all the math, we have actual software, and we have an open source data integration and query language tool that we call AQL. It's available on that website there, and so are the slides. The slides are kind of dense, so I would recommend maybe following along with them. And the outline of the talk is I'm going to review category theory very briefly, not anywhere near as dense as David. I will give an introduction to this area and then demonstrate the tool we have built. And then the second body of work I want to talk about is something that is hopefully relevant to functional programmers, which is how the databases in our theory model the simply typed lambda calculus. And then I have in the middle an optional assortment of material depending on time and what everyone's interested in that we could talk about. There may be something like 3 hours worth of material here. So this is the one slide review of category theory. One of the nice things about this particular project is you don't need to know that much category theory to follow along, just categories and functors. And I claim that you can still understand the talk even if you don't know category theory at this level, and there's ways to phrase it that are purely logical or what have you. But let's just review this really quickly because the word category and the word functor are going to come up a lot. So at the risk of offending David with my choice of words here, a category C consists of a set of objects, or rather a set whose elements are called objects, written obc. And then for every two objects in your category C, you have a set of morphisms or arrows between them. So we write this as your category C going from X to Y. So that is a set of morphisms from X to Y. And then for every object in your category, you have an identity morphism from an object X to itself. And then you have a way to compose morphisms in your category. So if you have a morphism from X to Y and from Y to Z, you can compose it using a little circle symbol to get a morphism from X to Z. And a category has to satisfy certain equations, these operations, the identity and the composition. In particular, the identity needs to be a unit for composition. So F composed with the identity is F, and identity composed with F is F. And then the composition operation has to be associative. So that's all categories are, just axiomatically defined mathematical objects like groups, rings, or fields. And the category that everyone here is probably the most familiar with is the category Haskell, or Hask, whose objects are types and whose arrows are programs, taking values of one type and returning a value of another type. But there's another category called set. David talked about this at length yesterday. The objects of set are, well, sets. And the morphisms in the category set are functions from one set to another set. So that's all. That's the brief introduction to categories. The only other thing that we're going to be talking about are functors. So these are morphisms of categories. And if you have two categories C and D, a functor F, it takes objects in one, C, to objects in the other, D, and it takes morphisms in one to morphisms in the other in a way that respects the identity and composition laws. So it is a homomorphism of categories, essentially. And there was a very nice talk just now about morphisms in general. Anyway, some example functors. There's a power set functor on the category set. It takes each set to its power set, and I'll leave it to the reader to figure out what it does on the morphisms. There's also a functor from the category Haskell to itself called list that takes each type to the type list of t. In fact, every type constructor in Haskell will be a functor of the, well, most type constructors in Haskell will be functors of functors from Haskell to Haskell. So anyway, that is all the category theory needed for this talk, so I will pause here to take questions. And it looks like there aren't any. So, I was going to say, David, you did a good job, but there is at least one question.
In the second line, you define category that has a set of objects. Then the category set has sets of, so do you mean the category set has a set of objects?
It has a set of objects, and each object is itself a set. So the
category set is a set of objects.
Well, a class. The category set has a class of objects. Each one of those is a set.
Then you have to tell which set theory you're talking about.
Which set theory? Let's assume the normal ZFC set theory for the purpose of this talk.
It doesn't have a class.
Okay. We can pick NBG or Morse-Kelly, whatever you want. It's not going to matter because we're only going to really deal with finite sets here anyway. So, you know, computers. Okay, any other questions? No. Okay, so to the fun stuff, the material here. So this is the slide. It is a graphical introduction to what we are doing. So we start in our framework by saying what a schema is, and this is an example schema in our framework. It is a directed, labeled multigraph and a set of equations between paths in that graph. So this example above the line has 3 nodes, emp, which is short for employee, dept, which means department, and string. Those are the 3 nodes. And then the directed labeled edges are manager, which goes from employee to employee, works, which means works in, an employee works in a department. It goes from employee to department. And then secretary takes a department to an employee. And then you have these 3 arrows, first, last, and name, which go from employee to string and department to string, because employees and departments have names. So that's just a directed labeled multigraph, but then you have these 2 path equations underneath it. So you can think of these as being data integrity constraints. So there's 2 written here. One says that works composed with manager equals works. So that means that each manager works in the department that they manage. And similarly, the other one here, works composed with secretary, is identity, means that each secretary works in the department they are the secretary for. So I think I made sense of those. But these equations are data integrity constraints, and let me tell you now what a database instance on this schema is. So that's an example instance, database instance, is written here below the line, and you have for each node, you have a table, and the tables have columns. Each table has a column of IDs. We can think of these as the IDs of your employees. There's 3 here. And the IDs of your departments. There's 2 here. And then there's 1 column for each edge going out of that node. So they're abbreviated here a little bit, but this means that employee 101 is, their manager is employee number 103. And 101's name is Al Aiken, and you also have a Bob Bowe and a Carl Cork, very imaginative names. The departments are CS and math, we all know and love, and then you have a table which is essentially a set of strings over here, but we usually don't write that one down because it's pretty large. And then you can check that these equations hold in this instance here, that you can see that each secretary does in fact work in the department that they are the secretary for. And so this is an example of our database schemas and our database instances, and the category theory is going to formalize this and make this intuition precise, and then give us some operations and constructions we can do on schemas and instances of this form. So I'll pause here and ask for questions.
So these arrows represent functions, right? Or the general physics relation, relations.
Right, so the question was, these arrows represent functions, and in relational databases you tend to think of relations, so there is a way to encode relations as pairs of functions. These are called spans, so if you really want to have a relation in this framework, you can have it. It just involves using two functions.
How does this deal with like nullable fields? So I assume eventually if you just keep going on manager, you'll get someone who doesn't have them.
Right, so the question was, how does this deal with nullable fields? And in this particular example, there is a manager 103 who manages himself. But if he had not managed himself, you're right that you would end up with essentially an infinite database instance. You'd have managers forever. And so you could add an equation that said, you know, you only have up to 100 managers. The attributes, the fields, or the arrows that go into string, there's another way to do nullability there, which I probably won't talk much about, but suffice it to say that comes up a lot in practice, and our tool can handle it appropriately. Other questions? Okay, then I will move on to the fun categorical shenanigans. So I just described an example of a schema and an instance, and on this slide I'm going to give a precise definition of what our schemas and instances are. So, and there's a variety of ways to do this, but I think the easiest way to do it is to say that a schema is a directed labeled multigraph with equations, and then that schema, it means, it has a denotation. That's what these church brackets, the double brackets, means, that each schema creates or denotes a category. So if S is your schema, then the category it denotes is bracket S. And the objects in this category are the nodes in your schema. So employee, manager, string. And then what are the morphisms between any two nodes? Well, that's the set of finite paths between the nodes up to the data integrity constraints, up to the equations that you had in your schema. So in this example, we can think of the morphisms from employee to department. You'd have one called works, but you wouldn't have one works composed with manager, because these two things are defined to be equal. So each schema denotes a category, and unfortunately, this question of if you have two paths in this graph, are they equal according to these equations, is not necessarily a decidable thing. So from the very beginning, all the software that we've written has to deal with some very difficult problems of decidability and computability. So, but on the positive side, that means that this language of schemas is in fact very expressive, that you can write data integrity constraints that encode things like Turing machines if you were so inclined, which I still wouldn't recommend. But anyway, so to complete the semantics, well, in category theory, you can't have a thing without a morphism of that thing. So what is a morphism between our schemas? These are functors. So each schema, in this case S and T, each of them denotes a category, church bracket S, church bracket T, and a morphism of schemas is just a functor between the categories. So basically, the slogan for this project is schemas are categories and schema mappings are functors. And people who work in ETL or data integration probably have seen many definitions of schema mapping that show up in tools like Informatica or DB2 or what have you. And there's a number of ways to write down schema mappings. One way is to just write down a function from nodes to nodes and edges to paths that preserves equations. But I'm going to give some examples here in just a minute of what these schema mappings are. So that's the schemas, the top part here. What about the bottom part, the database instances on these schemas? Well, if I have a schema S, it denotes a category, and then a database instance on that schema is just a functor from that category to the category of sets. And you can define it as a set of tables, one per node, that obeys the equations. So this slide is hiding a category and a functor from that category to the category of sets. And then there's a notion of morphism of databases, which are natural transformations, but we're not going to see those much in this talk, so I will ignore that. But one notational thing I want to mention is that if you have a schema S, then I'm going to write S-inst to indicate all the collection of all the instances which can be arranged into a category. So S-inst means the category of instances on the schema S. So I'll pause for questions here.
Could you say that you mentioned natural transformations? Could you see an equivalence in a data-only equation?
I'm sorry, I didn't quite.
So if I would apply a data-only equation to my database, is this the natural transformation you had been mentioned before?
So what I mean, so pick a schema S, and the database instances on it are functors to set, and so you can have natural transformations between them. What that corresponds to here are essentially mappings of IDs from one instance into the IDs of the other instance.
Yeah, sure, but it would still be the same schema, so only the data.
Yes, right. The data mappings. So the question was, well, I'll answer it. The data mappings are only between instances on the same schema. That's correct. Yep.
So are data mappings like mutations of the database?
The question was, are data mappings mutations of the database? I'm hesitant to use the word mutation because that implies like an effectful kind of thing. They are essentially mappings of IDs in one database to IDs in another database. And if you study relational database theory, they're exactly the database homomorphisms in their sense.
So your point is, as long as the two databases have the same schema, then you can basically copy one from the other, or will you change one on one? In one place it points at Al, the other one points at Carl, or is it just copying over so that?
So the question was to clarify what a database homomorphism was, and maybe to do that I'll just skip ahead because I wrote one down. So there's two instances on this slide on the same schema, one in the upper left, one in the lower left, and a morphism of database instances is just it's a natural transformation, which means it is an assignment from IDs in one to IDs in the other. It's not necessarily an occlusion. It's not necessarily anything, a surjection or what have you. It just takes IDs to IDs in a way that is natural, as the category theorists would say. Other questions?
So when you say modulo the path equivalences in S, is there a category theory notion behind that?
Yeah, so the question was, what do you mean by modulo the path equivalences in S? And that does unfold to a larger definition. So essentially what we have here is a finitely presented category. So you can have a finitely presented group or a finitely presented monoid or what have you. And what you do is you form equivalence classes of the paths through here, and then you merge the equivalence classes based on these equations. So another way to say that is you have a equational logic here, and you're building a term model and all of this stuff, and that's actually where the word algebraic comes from, but I'm going to kind of elide that for now. But did that answer your question? Okay, great. Anything else?
Is bracket S of xy equivalent to HOM of xy?
Yes, this is David likes to write HOM of bracket S xy. I just dropped the HOM. But yeah, it's the set of morphisms from x to y. Okay, so one more slide of math and then we get to more examples. So suppose we have two schemas, S and T, and they both denote categories. And we have a schema mapping between them, which is to say a functor, F taking S to T. Then from that functor S, we get three ways to move data from one schema to another. And we call these delta, pi, and sigma. And you've probably come across pi and sigma when you do functional programming as quantifiers. But anyway, the way this works is that one of the ways to migrate data is very simple. It's delta. It's this one here. If you have a mapping taking S to T, a functor S to T, then delta takes instances on T to instances on S. In other words, you give it a database on schema T, and it gives you a database on schema S. This is backwards from the direction of the functor, which is very counterintuitive. But it's easy to define. So here's F. It takes S to T. I'm using my mouse here to illustrate. So here's F going from category S to category T. Here is an instance I. I said I was a set-valued functor, so I is an instance on T. If you just compose these things, then by the way composition of functors works, and you can compose functors, I didn't mention that, but hopefully David did. You can compose functors, and when you do, you get a functor from the schema S to set. And so this delta operation is literally just composition. Given a functor from S to T, it gives you a way to take instances on T to instances on S. And the slides that follow will give examples of this. But hopefully the point is clear that this is a very simple thing to define, this operation delta. Then there's two other operations that go in the same direction of the functor. So the functor between schemas goes from S to T, and pi F and sigma F go that same direction. They take instances on S to instances on T. So they are the right and left adjoints to delta. So it's actually somewhat involved to write down explicit formulations of them. So the category theorists usually just say, oh, they're the adjoints, and then prove that they exist, and then that's all you need to define them. That's not quite all you need to actually implement them in software, but I'll give examples and then omit definitions of these two. But hopefully the point here is that from one schema mapping, you get three ways to migrate data. Two go forward, one go backward, and then the point of this project is essentially that you can use these data migration operations to do similar things to what you might use SQL or relational algebra or monad comprehensions or link to do, and that we claim there are advantages to this particular basis of operations. So I'll pause here. The next slides are examples of these. Any questions? Okay, so hopefully this will clarify some of the dense definitions. So here's a functor F, it's a schema mapping. It takes this schema S on the left. The schema S has two nodes, N1 and N2, and strings and integers. It takes these two nodes, and it's a functor into this schema here on the right, which just has one node, N. So N1 and N2 both get mapped into N. And then these edges get mapped straight across. So name goes to name, salary to salary, age to age, int to int, string to string. So just the two nodes in the middle get mapped to the one. It goes from left to right. And the slide before this said you get an operation that takes instances on this schema to instances on this schema, right to left. So what's an example of that look like? Well, if you have an instance on the right, say this one here, it has one table because there's one node in this schema. It has three rows, Alice, Bob, and Sue, and then it has columns for name, salary, and age. How do you move data on the right to data on the left according to F? And if you work out all the details, you find that this is doing essentially projection. It's taking these three columns and separating them into two tables. So we have to have two tables here on the left because there's a node here and a node here, two separate nodes in this schema. And it projects the information out and creates essentially new IDs here. So the IDs in this framework are meaningless, but the data is not. So Alice, Bob, and Sue came across, but you have some fresh IDs in these tables here. So I'll pause for questions here. This is usually the place. Yep, lots of hands. Okay. Yes?
So are F and delta F, are those adjunctions?
So the question was, are F and delta F adjunctions? And the answer is no. So given F, you get a delta F. And the adjoints to delta F are other operations that I'm going to show next. They are the pi F and the sigma F. So each functor induces three operations. Yeah. Other questions?
Is it a unique way to do it, or was it somehow chosen arbitrarily, or is it somehow universal?
So we defined, the question was, is this the unique way to do to define these things? And the answer is that given this particular way of defining delta, which we like because it's very simple, it's just composition, it's a fact of category theory, which I'm sure David mentioned, that the adjoints are defined up to are unique up to isomorphism. So given this delta, the adjoints have to be these things here.
No adjoints so far, right? It was just about the delta.
That's true. The next slide is the pi, and then the next slide is the... So these two guys here are the adjoints to this one here. Yeah. Yes?
Was it intentional that this projection was not preserving the ability to join it together again?
The question was, is it intentional that this is not a lossless decomposition, that you can't join these two things back together? And the answer is yes. The reason is that there is no connection in this schema between N1 and N2. And for that reason, you cannot join N1 and N2 back into N.
You could have designed it that way that the loss information was not.
Right. In fact, this slide here, suppose you have a similar schema which has an edge from N1 to N2. Database people like to call these foreign keys. Taking N1 to N2, and then that means in your instance you have a column here, F, that connects the tables together. In this case, if you start over here on the right and you delta back, then that extra column will be populated with exactly the information you need to join the two tables back together. Other questions on delta?
I don't understand how F would be defined.
How do you, so the question was, how do you define F? Because it's not unique. And you're right, there are many possible Fs between these two schemas. So you pick the F that you want. And in this case, I told you that the F that I want takes N1 and N2 to N. And then given your choice of that, you get back delta F, sigma F, and pi F. But, and there are ways to look at these things and kind of guess functors, but in general, someone has to pick, they have to tell you which schema mapping they want. And there will be many.
Something hard time imagining an F as a cake, the left-hand side there to the right-hand side, or what given the thing on the left, what would, if not producing the thing on the right, what would it be?
So you could imagine, there's lots of functors out there, right? Because one thing, suppose you wanted to go from this schema on the left to itself, are there more than one? Is there more than one functor from this thing to itself?
You can do Cartesian product. You can do a Cartesian product with
Yeah.
There's several functors from the left one to the right one. The salary could go to age by
So David says there's several functors from the left to the right because you could take salary to age, for example. That's true. Thanks, David. Sorry? Four functors from the left to the right, says the mathematician, and I'm inclined to believe him. Yep. Well, to give a functor, you have to give a mapping for each edge. So you have to send n1 somewhere, and you have to send n2 somewhere. That's part of the definition of what it means to be a functor. Okay, other.
So sending n1 to n1 and n2 to n is like you could just say, well, I'm going to take I'm going to take 1 and 4 and and 2 and 5 and 3 and 6, or you could do any combination, I guess, and just kind of mix them up. Is that kind of the point?
Well, you shouldn't. When we're talking about schema mappings, you shouldn't be thinking about anything below the line, right? So you have a category here, or a presentation of a category here, and we have a presentation of a category here. We just have to give a functor. The fact that delta f is a projection and pi f is a product and sigma f is a union are they're mathematical theorems. But when you're thinking, how do I get a mapping from one schema to the other, the only thing you have to work with is the data above the line.
You can say n1 and n2 go together, but you don't have to say like how the IDs or the values line up. You're just saying they just go there.
Right. So to rephrase, the functor just says where n1 and n2 go, and in this case they go to n, and then that's it. The fact that it was a projection is a theorem that David proved. Okay, other questions? I'll move on to the adjoints to this thing.
So are conceptually the string and int nodes also tables, and just a shortcut that you write them in line?
Yeah, they are conceptually. The question was, what happened to string and int here? And the answer is they're very big tables. And so here I wrote them down on this slide, but then I've elided them because they just kind of take up space. Okay, then I'll move on to the other operations. So if you could just project using this framework, that'd be kind of boring, but luckily you can do other things. So this slide shows the right adjoint to delta f. So given the same schema mapping, taking n1 and n2 to n from left to right, the pi f operation takes instances on the left to instances on the right. So here's an example where the two tables, each one has 3 rows. It's still Alice, Bob, and Sue. This is the same example instance as before. And the pi f operation, what do you get over here on the right is you get the Cartesian product. So 3 rows times 3 rows equals 9 rows, and you have all the possible combinations of the rows. Questions here? Yes?
My understanding is that the adjoint of a functor and another functor between the same object going in the opposite direction. Is that right so far?
Right. So you'll notice here that pi f went from right to left, and delta f went from right to left, and then pi f goes from left to right. So the adjoints go reverse direction of the thing they're adjoint to.
Okay, and I'm sure that this is wrong because it doesn't make sense to me, but it seems like this the right adjoint or the adjoint of pi should be a functor from sets to your first category also.
Yeah. So the question was to clarify what's adjoint here. So I think what you're thinking of is you're probably thinking of an adjoint to this functor from t to set, which would have to be something from set to t, but that's not the adjoint relationship that's going on here. What's happening is that delta f, it's a functor from the category of instances on t to the category of instances on s. It has 2 adjoints, left and right, and they go from the category of instances on s to the category of instances on t. And I saw your smile, so that's good. Okay. Other questions on pi? No. All right, just one more, because there's only left and right adjoints, fortunately. Yeah. Okay. So same functor f goes from left to right. N1 and N2 go to n, and this one goes in the same direction as pi. So it takes instances on the left, instances on the right, and this one does essentially what is an outer disjoint union. So you start with these 2 tables on the left, N1 and N2, each has 3 rows. You'll notice they're not union compatible. That's the slang. And so when you union them together, you end up with null or fresh made up values in the table here on the right. So in SQL, this would be an outer union kind of operation. Questions here?
Each null has its own subscript. Are they each their own object in the category? Or?
So the question was, why do each null have its own subscript? And the answer is they are meant to represent distinct null values. So this is a bit divergent from the way SQL handles null. But mathematically, they have to be distinct values. If they were all the same, then that would not be what the definition of sigma is. So these are called labeled nulls in database theory. And you'll notice there's as many of them as possible. They're freely chosen.
Do any databases use labeled nulls?
The question was, do any databases use labeled nulls? And the answer is, I really wish they did, because that's the mathematically correct way to do them. SQL does not. Some data integration tools, especially the ones that come out of academia, do use labeled nulls. In the software I'm going to show you, our software uses labeled nulls. But yeah, I wish. Yeah.
What is the advantage for the customer of using labeled nulls?
The advantage for the customer.
That can be a fellow programmer too.
Right. So here, I think the answer is just that if these weren't labeled, if you didn't label the nulls, you're making an assumption that the nulls all represent the same value. But in fact, the intention here is that the age of Alice could be different from the age of Bob. So SQL goes through all these hoops like three-valued logic and all this crazy stuff. But really, the advantage is we want to say that there's a value for Alice's age, and it's different from the value for Bob's age. So we want to label them. And I think that's a better semantics for nulls than what you get in SQL. You could use a question mark instead of null. But yeah, different symbols. Yeah. Okay. Other questions? Yes.
To confirm, like sint means the category or the whatever of every single possible combination of data that might be in a schema called S.
Right. So sinst.
Possible database that could be within the database.
Yep. Pick a schema S and consider all the instances on it. That's a set of them, but they can be arranged into a category when you consider the morphisms between them, and that's exactly what sinst means. So in fact, these operations, I'm only showing you part of what's going on, because here I'm telling you sort of what happens on the objects in this category. But if you were to give me a morphism of database instances, this thing would also run delta, sigma, or pi on the morphism of instances. So there's more to it that I'm not showing.
So when you say sigma f takes an S instance to a T instance, are you talking about one instance, or just like any instance in S, it can always map into a T instance?
Any instance in S, it gives you back a unique instance in T up to isomorphism. Yep. And ditto for pi and delta. Okay, other questions? No. Yep, one more.
So in this category, do you also have implicitly assumed objects for joins, like joins that in like SQL joins?
So that's a good. So the question was about joins and that kind of thing, and the answer is that the way you perform using your schemas and your mappings in such a way is that they result in joins. So the category of instances doesn't say anything about joins, but you can use the pi operation, for example, to compute a join. So here's the slide I showed before, where it's the same schemas, except the one on the left has a foreign key from N1 to N2. And here's an example instance. And when you do the pi, and in fact when you do the sigma, both of them, you find that they will join along this column. So here you see 4 goes to 4, and 5 goes to 5, and pi and sigma, they do a join here. So you want joins, you write schema mappings that do joins, and you use pi, and then you've got your joins.
Kind of like you have to have a categorical relation definition where it says 4 goes to 4. Is that how you kind of like end up like forcing it to be mapping 1 to 1 as opposed to like the Cartesian product that you had before?
So I guess the question is, why is it a join in this case? And the answer is, when you have a foreign key like this in your schema, you find that you just work out the definition of pi, and you find that it will, in fact, do a join. And there's a theorem that says you can do all joins in the sense of SQL in this way by choosing suitable functors. Okay, more questions.
I'm just guessing some form of limit other than product in the category. Disjoint with foreign.
This is a limit, and the sigma is a colimit. And there are other limity things you can do in the category of instances. They have limits and colimits. And they form a topos and all this stuff that I won't get into. Yeah, other questions?
So how would they model a restriction?
How would you model a restriction? You mean like that a particular function is surjective or injective or something like that?
Simulation algebra restriction. Or basically the where statement in SQL.
Which statement?
The where statement.
The where. Yes, so you do that by, the question was, how do you do things like filtering conditions? And the answer is, basically these equations in the schemas play that role. So to get from one schema to another by way of a filter, you may have to create an intermediate schema that has some equations in it, do a pi and then a delta, and then the result will be a filter. Or we lately figured out there's a nice, there's a syntax people can write that looks like SQL that then translates into deltas and pies. So the practical answer to your question is, if you're using our tool, you just write a where statement, and then you're good to go.
When you do a where, you're actually not like joining it. You're literally just picking another instance in the category that happens to already happen.
So it,
go through the way you want it technically.
Okay, I'll just I'll restate. So the where, the filtering is a conceptually distinct operation to joining, right? So in relational algebra, you have a filter and you have a join. Or, well, anyway, they're conceptually distinct things that are going on that often get conflated or used at the same time a lot. So, okay, we've used up most of the the lecture on the first 10 slides, so the other 3 hours of material will have to wait. But there is something here I wanted to point out, which is monads, because functional programmers seem to love their monads. So, so they tell me. I said there were adjoints here, right? You had delta f and sigma f and pi f were adjoints to it. And every monad arises from an adjunction, and every adjunction induces a monad. So what are the monads that are lurking here? Well, the example I'm showing here is the unit of the sigma delta adjunction. So if you start with your data here on the left, and you sigma it forward, like I showed before, and then you delta it back to get onto the same schema you started with, the unit, it's a data mapping, a morphism of database instances from where you started to where you ended up. So in this case, it's not quite an inclusion, but it's an injection, if you will. It takes the original data, 1, 2, 3 here, and maps it to A, B, C, and it takes 4, 5, 6 over here and maps it to D, E, F. So the units and the co-units and all those fun things that come up in Haskell, they come up here too. They're just morphisms of database instances rather than things you write in Haskell. So in practice, what this means is that this formalism has very nice provenance very nice provenance properties, because this is a way to relate where you started, the data you started with, to you move it around, and then you can figure out where the data landed. So, yes, question?
Your schema changed here, right? ID is no longer an int. You changed your schema.
The schema is the same. The data is different. So we started here with this one on the top. We sigmaed it forward, and then we deltaed it back, and we arrive on the same schema, the same 2-node schema. And then the morphism from your original instance here to the one that's been sigmaed and deltaed here is an assignment of these IDs to these IDs and these IDs to these IDs.
Yeah, for your question, there was no morphism to the ID pointing directly, so you don't have to preserve that.
Okay, I'll since time is running short, I will I'll show you the tool and then take some questions, and then if you want to know what this has to do with lambda calculus, you can ask me offline because it's really kind of cool. Okay, so if you go to our website, you can download a jar file or some pre-built binaries, and you run it, and it pops this thing up, and you'll find in the examples menu, somebody put a LambdaConf example in here, that goes through the code that corresponds exactly to the slides I just showed you. So let me make this a bit bigger. So the tool does some things that I elided in the slides, but morally, the slides are a good introduction. In particular, the tool associates a type in a programming language to the nodes string and int like I was showing. So here, the tool, it's written in Java, and the intention is that associated with the data types like string and int are types in a programming language. So here we say string and int correspond to Java's, but mathematically we can put any programming language sort of underneath this thing. So that's what this first thing called a type site is. You sort of define your computational universe. Then you can go in and do the fun things like define schemas for employees. So this is a text-based tool. You just write down, for example, my entities. That's what we call the nodes in these schemas are employee and department. And you say my foreign keys, this is database slang. You have the three that I mentioned, manager taking employee to employee, and secretary taking department to employee. And you write down the path equations that you want, and if you wanted to avoid this infinite manager situation like was alluded to earlier, you can add an equation like this one here, but you don't have to, it's commented out. And you give some attributes. These are like foreign keys, they just end up in types. And then the tool will either pull in data for you from, say, SQL or CSV, or you can just write down as text an instance on that schema. And the way we do that is as a set of equations. That's the reason the whole talk is called Algebraic Databases is that this instance here is actually a thing called a algebraic theory, but be that as it may, here are three employees, 101, 102, 103. Here are two departments, Q10 and X02. And here are a bunch of equations that say what the entries in the table are. And you run this thing, and you can look at it, and it shows you here in the viewer that you have Carl, Cork, Al Aiken, and Bob Bowe in your table. And it's picked values for IDs. So one of the things, when category theory is involved, you have to be a little careful about identity and isomorphism, but suffice it to say, your data is all intact in this little table. I will show now the sigma delta data migrations. So here are two schemas, S and T. They correspond to what we were showing in the slides, the schema mapping. So two entities, nodes, N1 and N2, one node in schema T, and here's the foreign key in between N1 and N2. You write down a mapping by just saying, for example, N1 goes to N, and N2 goes to N, and in this case, we have the foreign key. You say that the foreign key goes to the zero-length path on N, and then attributes get mapped similarly. They involve lambda notation for reasons I won't go into here, but you're welcome to ask about. And then, this thing will do, for example, it'll compute your sigma for you. It'll compute your delta. It'll even compute the return or the bind of the associated monad. And right, you can examine it. Here's an instance I to start with, like I showed in the slides. And you sigma it, and just like in the slides, because of that foreign key between the two nodes, it ends up joining them. And then when you delta it back, you find that it just projects while preserving the relationships. And then if you wanted to look at the unit of the monad, it will show that to you. And anyway, there's all kinds of interesting stuff in here. And this open source tool, it was developed at MIT with David's generous support. And now there's a startup company that was recently spun out of MIT that's trying to turn this thing into a real industrial strength data integration tool. And that's a long road, but I will go ahead and conclude here to take time for questions. So we're looking for collaborators, and please download the tool, play with it, send bug reports, feature requests. I'm happy to talk offline, and if you're feeling brave and want to try to use this technology to do data migration or data integration at an industrial scale, we are charged with technical validation of this thing by our government agencies that are funding its commercialization. So we're looking for collaborators for pilot projects and other reasons as well. And yeah, check out the website. So, thanks. I'll take questions now.
What's the benefit of doing this over any of the other standard ways of doing calculus?
What are the benefits of doing this thing? So the claim is that this tool does high assurance data migration and data integration. So what you can't do with this tool, for example, is materialize an instance on a schema that does not satisfy the equations. So when you say, I have a functor from schema S to schema T, there's a theorem prover embedded in this thing that actually checks that what you wrote down was a functor. And then that means that when it migrates data, it's guaranteed that your data integrity constraints get preserved when you do the migration. So the claim is that this is this tool catches at compile time the kinds of mistakes that existing tools like Informatica will catch at runtime, if at all, and that for that reason it's more agile. Yeah. Yeah. Other questions?
I mean, I know now it's not like fully optimized in the sense that like Postgres or whatever it is, but does this extra information that you have in the form of like mathematical purity and such allow you to potentially make like better optimizations in the future?
The answer is, does all this category theory allow you to do better optimizations? The answer is yes. There's all these algebraic identities you have because sigma is a colimit and therefore it preserves sums, like those, you get all these algebraic identities out of the category theory that you can in principle use to do query optimization. And if you want to do that for us, that would be great. Good paper there. Other questions? No. Okay, well, thanks everyone. And we're about 5 minutes early, so yeah. Sorry?
You've got 5 minutes.
5 minutes, keep talking. I don't know. What did the sponsor say? Is it time to stop, or you want to hear me?
Yeah, like 4 minutes.
4 minutes. Okay. All right. Then in that case, I will talk about the second part of, oops, I'm going the wrong way. The second part of what I wanted to show you guys, which was that that category of instances on a particular schema. So fix a schema S and consider the category of all the instances on it. That category is Cartesian closed. That means it is a model of the simply typed lambda calculus. So those of you in Dana Scott's session got to hear about one kind of model of the untyped lambda calculus. But basically, there is, if you have a schema like this, just two nodes and an edge between them, all the operations that you would expect to be able to do in the lambda calculus, like take products and take exponentials, you can do them with the instances on that schema. So for example, what does the unit instance on that schema look like? It is an instance that has one row in every table. And you can prove that it is a terminal object in the sense of category theory because every instance in the category maps uniquely to that instance by virtue of it having exactly one row. And then this story repeats. You can do products of instances this way, and you can do exponentials of instances in this way. Actually, you get more than Cartesian closure. You get coproducts, and you get a sub-object classifier, and you get all these interesting constructions on your instances. And so another reason we like this is you get a very rich calculus of operations that you can do on your instances, and sometimes people like to product their instances in practice or what have you. But okay, that's the very quick abbreviated end spiel, so I will end for real this time. Thanks.